Hi everyone. In this video we're going to talk a little bit about the determinants of elementary matrices and see what kind of information that can give us about matrix invertibility and solutions to linear systems and all kinds of other stuff. So let's remember that there are three kinds of elementary row operations. There's the multiply a row by a scalar. We'd write it like k times ri, where I is the index of the row that we're looking at. This is what an elementary matrix that executes a row operation like this might look like. In this case, E1 is a matrix that multiplies the second row of another matrix by the scalar k for some k not equal to 0. Now, we talked before about the determinant of a diagonal matrix like this one, where all the entries on the off diagonal are zeros, is just going to be equal to the product of the diagonal entries. So that means that the determinant is equal to 1 times k times 1 times 1. So the determinant of an elementary matrix that serves to implement this type of row operation is always going to have value equal to that scalar. The second type of elementary row operation that we probably use the most frequently is that one where we add a multiple of one row to another row. And those look like Ri plus or minus some constant times Rj. And here's an example of one matrix that does that. So in this example, I have here a matrix that's going to implement the row operation that would take row 3 and add k times row 2 and put that back in row 3. Now this is not a diagonal matrix, but it is a triangular matrix because all the entries above the diagonal are equal to 0. So it's a lower triangular matrix. And we've seen already that the determinant of a triangular matrix is just the product of the diagonal entries. So the determinant of this E2 matrix is just equal to 1 times 1 times 1 times 1. This is just equal to 1. And no matter where that k shows up, because there's only one of them, that's always going to be the case. We'll either have an upper triangular or a lower triangular matrix for this type of row operation. So that makes it possible to say that the determinant is always going to be 1. The last one is where we do a swap. If we swap row I and row j. So an example of what that looks like would be something like this. So this matrix would be the one that would implement swapping rows 2 and 4. It's a good exercise to take a minute and actually compute the determinant of this one. You'll find out that the determinant of this and every row swap matrix is going to be -1. Alright, so here are the things we know. If we multiply a row by a scalar, then we change the determinant by a factor of k. If we add a multiple of one row to another row, we don't change the determinant at all. And if we swap two rows, the effect of that is going to be negating the determinant. Let's see an example where we implement some of this stuff. So in this example, I want to compute the determinant of A, and I'm going to do that by, instead of doing cofactor expansion, using some of these elementary row operations to simplify the calculation a little bit. So I'm just going to start by implementing that Gauss-Jordan algorithm to try to get some more zeros in this matrix. So I'll do row 2 minus row 1 and row 3 plus 2 times row 1. And that will give me this. And from here, I see that if I make one row swap, so let's see, I'm going to do row 2 and row 3, I'll get a pivot in the 2, 2 entry, and the result will be this. And now this is an upper triangular matrix, and it's easy to compute the determinant. So let's call this A prime. The determinant of A prime is 2 times 2 times -5. So that's -20. And if I go back and look at my row operations, I need to keep track of those and how they affect the determinant. So when I did this, I changed signs. And when I did these, since I was adding or subtracting a multiple of one row from or to another, I did nothing. So the determinant of A prime is negative 20. Following through the row operations, I see that I executed a row operation that does affect the determinant, as we discussed above, and it changes its sign. So that means the determinant of A prime is the negative of the determinant of A. So the determinant of A is 20. Sometimes a few clever uses of row operations can save a lot of cofactor calculations. So always be on the lookout for those. Now that we know something about the determinants of those elementary matrices, let's think about what they can tell us about invertibility. Let's take a moment to recall how we go about finding the inverse of a matrix. The way that procedure works is we start with our matrix A put together with an identity matrix I to form this augmented matrix, and then we perform a sequence of row operations, which we can encode into these elementary matrices, and then our row operations are essentially just matrix multiplications. And once we have finished all of those row operations, what we end up with, assuming that A inverse exists, is the identity matrix on the left-hand side and A inverse on the right-hand side. Put another way, this says that En times all the way down to E1 times A is equal to I, and if we do En times all the way down to E1 I, we're going to get A inverse. And since multiplying by I is just like multiplying by 1, we really don't even need to write that. And we even computed a couple of inverses by playing around with stuff like that. Now let's take a moment to think along the lines of the determinant. The determinant of the identity matrix is equal to 1. And the determinants of the elementary matrices, they are all non-zero. So that means if we can use elementary row operations to convert A into the identity matrix, this equation will be true, and the determinant of A, whatever it is, it can't be 0. So if A inverse exists, the determinant of A can't be 0. If the determinant of A is 0, then the inverse doesn't exist. Or put another way, if the determinant of A equals 0, A inverse doesn't exist. And what does this tell us about the corresponding linear system? If the determinant's not equal to 0, then A inverse exists, and AX equals B has a unique solution. And if the determinant of A is equal to 0, that's not the case. Either AX equals B has no solution, or it has infinitely many solutions. So just to summarize what we've done here, we started by figuring out what the determinants of elementary matrices are, then used some of those properties that we talked about to help in computation of a determinant. We used row operations to get to a triangular matrix, and then it was easy to compute the determinant by multiplying the diagonal entries. Finally, we used this idea of elementary row operations being able to produce the inverse of a matrix to prove that a matrix is invertible exactly when its determinant is not equal to 0. And there are loads of other things that a determinant being 0 or not can tell us. Here's a list of some of them. So if we take an n by n matrix A, then all of these conditions are equivalent. So that means they're either all true or they're all false. Some of them we've already talked about, like if the determinant of A is not equal to 0, then A inverse exists. And that's the same thing as saying that the row reduced echelon form of A, which is what this stands for, reduced echelon form of A, is equal to the identity matrix. That also means that every linear system that has A as its coefficient matrix is going to have a unique solution. In particular, the homogeneous one will have a unique solution as the 0 vector. And this is the same as saying that A has n pivot positions, right? That's how we get to our reduced echelon form of the identity matrix. And then finally, the columns of A, if we're considering them as vectors, form a linearly independent set of vectors. And since there will be n of them, that means it's basis for Rn. And that's a fact that's also true about the rows. So if you take the rows of a matrix that has a non-zero determinant, those rows considered as vectors will be a set of n linearly independent vectors, and so will form a basis for Rn. Okay, so that's a lot. I recommend staring at this list of conditions for a little while and making sure you see why they all are saying the same thing. And in the next video, we'll see a trick that uses determinants to compute the inverse of a matrix.